Good afternoon. Welcome to the second lecture. In the first lecture, we have introduced the notion of the metric space and considered several examples of metric spaces. In particular, we considered the space Rn with several metrics. So here we just take the absolute value and sum them up. Here we square them, then sum them up and take the square root. As you might guess, there is nothing special about this square and the square root. And this kind of metric can be considered for more general index. That is what we going to do. Rho sub p will be this kind of a metric. So we take the absolute values, raise them to the power of p, then sum them up, and then we take the pth root out of the whole sum. We consider p is greater than or equal to 1. Let's briefly check the first two axioms of the metric. So does the first axiom hold? So this expression, the metric equal to 0, if and only if x equals to y. Is this the case? Yes, it is the case. What about the second one? If we flip x and y, do we get the same result? Yes, because of this absolute value. Well, as usual, the third axiom, the triangle inequality, is the most complicated. And to prove it, we need to prove the following inequality. We need to prove that we need to prove this inequality. We need to prove it for any 3 points from our metric space. Well, not metric space yet, we haven't proved that it is a metric from our set. The idea is pretty much the same as in the case when p equals 2. So to simplify this, we'll make a substitution to end up with the Minkowski inequality. Minkowski inequality, which is ak plus bk to the power of p raised to 1 over t. Exactly the same, we've made exactly the same substitution as we did in the previous lecture. And here we have ak to the power of p. P greater than or equal to 1. Well, you might guess why we only consider the case when p is greater than or equal to 1. The reason for this is quite obvious. This inequality does not hold if p is between 0 and 1, and this is an exercise for you. Fails if p is less than 1. This is an exercise. Okay, so in the previous lecture, when we proved the Minkowski inequality in a specific case when p equals 2, to prove it, we use an auxiliary inequality which we call the Cauchy-Schwarz inequality. So here, in the general case of Minkowski inequality, the idea is pretty much the same. We need some auxiliary inequality, which is in this general case called the Hölder inequality. So we first prove this Hölder inequality. Which is stated like this. AK times BK, the sum from 1 to n, is less than or equal to sum of AK raised to the power of p times sum of BK's raised to the power of q where p and q are greater than 0 and 1 over p plus 1 over q equals to 1. First of all, you might ask why we state the Minkowski inequality for the value of p greater than or equal to 1, but for the Hölder inequality we only cover the case when p is strictly greater than 1. But if you look at the Minkowski inequality when p equals to 1, this is just the inequality between the absolute values. So it's just the usual triangle inequality. So for p equals to 1, Minkowski inequality is quite straightforward. We only need to prove it in the case when p is strictly greater than 1. And for this one we will use the Hölder inequality. Okay, let's get started. Proof. First of all, let's note that if this inequality holds for a and b, then it also holds when a replaced by a times some scalar and b replaced by b times some scalar. Let me call it asterisk. So this inequality holds for a, well, vector a and vector b, if and only if it holds for alpha times a and beta times b for every real numbers alpha, for every, well, yeah, real numbers alpha and beta. Well, in fact, if instead of A here you will write alpha A, then you can take this alpha out of the sum. Here it will be raised to the power of p, but then we take the pth root and it will be alpha. Let's rather go with for positive. The same story is here. If you replace b by beta b, then you can factor this beta out, and the same story is here, but even simpler. So, this property, by the way, is termed, in other words, this inequality is homogeneous. Which is exactly what I explained in the first sentence. So you can scale the vectors and the inequality will be still will be true. Okay, so having this property, having that this equation is homogeneous, we can assume, without loss of generality, we can assume that sum of ak raised to the power of p is 1. That's what we can assume. And the sum of b's is 1 as well. Well, if it's not 1, then we can always find the scalar alpha and the scalar beta such that we shrink or dilate the vector such that this sum will be 1. Well, having this assumption, we only need to prove that the left-hand side is less than or equal to 1. This is what we need to prove. To prove it, let us consider the function y equals to x to the power of p minus 1. For x greater than or equal to 0. Or equivalently, if we take the inverse of this function, it will be x equals to y to the power of 1 over 1 minus p. But having this relation between p and q, we can easily see that this index 1 over p minus 1 is nothing but q minus 1. Let's now draw the graphs of these two functions. This is what we have. This is y equals to x to the power of p minus 1. Well, since p is strictly greater than 0, p minus 1 is strictly, since p is strictly greater than 1, p minus 1 is strictly greater than 0, this is what kind of shape, this kind of shape we have. Now, if we take any a on the x-axis and any b on the y-axis, and if we denote these areas by S1 and this one by S2, then we can conclude that S1 times S1 plus S2 is less than or equal to A times B for any n. Yeah, sure, thank you. Greater than or equal to. Greater than or equal to. Because what? Yeah. So in this particular case, A and B is the area of this rectangle, and we have an extra bit. Now let's try to express S1 and S2 in terms of A and B. Well, S1 is the area below the graph. So S1 is then an integral from 0 to A of our function, which is, well, nothing but a to the power of p over p. So this is this area below the graph. Well, S2 is in fact an area below the graph as well. This graph. So we flip the axis over and we can write S2 as an integral from 0 to b of the inverse of this function, which is y to the power of q minus 1 dy, which is similarly b to the power of q over q. We have proven that a to the power of q over q, a to the power of p over p plus b to the power of q over q is greater than or equal to a times b. Well, we have used here that p and q are related, so they are conjugate of each other. And we also used here that a and b are greater than or equal to 0 for every a, b greater than or equal to 0, and 1 over p plus 1 over q equals to 1. So we have proved this numerical inequality, numerical for numbers. And now we will use this inequality to prove our Hölder inequality. So first of all, instead of A and B, we substitute AK and BK. And I will take the absolute values as well. So less than or equal to AK to the power of P So we have this inequality for every k. Now, since we have it for every k, let's sum all the left-hand sides and right-hand sides for k from 1 to n. But according to our assumption, what is the value of this sum? It is 1. And what is the value of this sum?
1.
It is 1 as well. So what we have here is 1 over p plus 1 over q, which is equals to 1 by our assumption as well. And so we are done with the Hölder inequality. Now let's prove the Minkowski inequality using this Hölder inequality. So let's take the left-hand side of the Minkowski inequality and see what we can do with it. I will not raise it to the power 1 over p. We will first prove inequality and then take the root. So what I want to do is to write this as sum the same term but raised to the power 1 minus p times ak plus the same term but with bk instead of ak. This is how we can write the right-hand side, the left-hand side of Minkowski. Well, over here we have this sum, and every element of this sum is a product of two terms, which looks like a perfect situation to apply the Hölder inequality. And in the Hölder inequality, I will take this one as AK in Hölder and all this one as a BK, because I want these to be raised to the power P, and for this one we will see what we can get. So by Hölder, this is less than or equal to sum AK to the power of P 1 over raised to the power 1 over P. So this is taken as a first term in Hölder and this one as a second. P minus 1 and all raised to the power of Q 1 over Q. So we have applied the Hölder inequality for the first term for this expression. Now we will do the same, we will apply the Hölder inequality for the second term, and again, as a first term, as an AK in Hölder, we will take BK, and this will be the second term in Hölder. Similarly, we have what we get. Well, first of all, let's note that if we wouldn't have this term and this term, then we are okay with the right-hand side, because this is what we want in the right-hand side of Minkowski. So we need to get rid of these terms. They are the same, so we can divide the both sides of this inequality by this expression. We, of course, can assume that this is not zero, because when this is zero, the Minkowski inequality is trivial. So now we divide the both sides of that inequality by this expression. By the way, here, over here, we have p minus 1 times q, but what is it? What is it? So we know that q is p over p minus 1. So p minus 1 times q is then just p. So on the left we have ak plus bk to the power of p and the index of the power will be 1 minus 1 over q, which is, well, nothing but 1 over p, and we know that it is less than or equal to all what's left on the right hand side. And again, as we already said, this is nothing but 1 over p. So let me just rewrite it, and this will be the Minkowski inequality which we have proved. Well, this is exactly what we wanted, as required. So we have proved the Minkowski inequality. From this Minkowski inequality, we can conclude that the function rho sub p is metric in fact. So we conclude that a pair Rn with the metric rho p is a metric space. Is a metric space. Well, as we already discussed a little bit, when p equals to 2, we get the usual Euclidean metric. When p equals to 1, we get rho 1, which we have considered in the first lecture. We have also considered the metric which was denoted by rho infinity. And in fact, it can be shown that that rho infinity is also related to this rho sub p. So that will be another exercise for you. Exercise is to show that rho infinity of xy equals to the limit of rho p of xy when p tends to infinity. So this rho infinity metric is the limiting case of this rho p for every x and y from Rn. So let's consider this set of continuous functions on an interval AB. On the previous lecture, we have introduced one metric for this space, and that metric was the integral metric. Let's call them F and G. So this is the metric which we introduced last time. Well, similarly to the case of Rn, there is nothing special about ones here. We can raise this absolute value to the power of p and the whole integral to the power 1 over p. And again, for p greater than or equal to 1, this is a metric. To check that this is a metric is left for you as an exercise. And the proof is fairly similar to the one we have done right now, but you will need an integral version of Minkowski inequality. Let us now generalize Rn to the situation when vectors has not finitely many, but infinitely many components. So from vectors in Rn, we will go to sequences. Let us take, that was one example. Let's go to the other example. So let L be let's rather go with L infinity. So by this subscript, we will denote the metric which we will introduce on this set. Let L infinity be the set of all bounded sequences x, well, with coordinates x1, x2, x3, and so on up to infinity. So infinitely many coordinates. Well, such that the set of all bounded sequences x, that is. So what do we mean by boundedness? It means that if we take the absolute values of all coordinates, then supremum of them is less than infinity. So they are bounded. And we consider the metric on this space to be the infinity metric. So as in the infinity metric, we take the absolute value of the difference and then take supremum of this. Now let's take the same set of sequences, of bounded sequences, and introduce various norms on it. Let L sub p be the set of all p-summable p-summable sequences, which means that if we take any coordinate, every coordinate of this sequence to the power of p, if we raise the absolute value of xk to the power of p, and then sum over all indices, then this number is finite. And as you might guess, the metric which we introduce on this set will be the p metric. And as usual, p is greater than or equal to 1. Before we even start to discuss the axioms of the metric, we have to discuss why is this expression finite. So in fact, what we have here, we have the sum of infinitely many terms, and a priori, it is not guaranteed that this sum is finite. We can take the Minkowski inequality, which we proved before for Rn. Another example will be again on this set of functions on a given interval AB, but now we will drop the conditions of continuity. Let M on AB be the set of all bounded functions. Be the set of all bounded functions. Well, on the bounded functions, when we consider the case of continuous functions, we use the fact that a continuous function on a closed interval, it attains its maximum and minimum. So we could speak about maximum of the function. Here we just have the set of bounded functions. So in fact we cannot speak about maximum. And let me show you the example of a bounded function, but which doesn't attain its maximum. So let f be the function on 0, 1, given by f of t equals to 0, and here say 1 minus t when t is 1 on n and is a natural number, and 0 otherwise. So let's try to sketch the graph of this function. So first of all, it's 0 almost everywhere. It's 0 almost everywhere. When n is 1, then t is 1 and the function is 0. When n is 2, then t is half and the value of the function is half as well. When n is 3, then t is 1/3. The value of the function is 2/3. So 1/3 is pretty much over here, and the value is 2/3 somewhere over here. When n is 4, this is half, third. When n is 4, t 1 over 4, and 1 minus t is 5 on 4, or 5 on 4, 3 over 4. And this one is 3 over 2, no, 3 over, oh, okay. 1/3, 2 over 3. 2 over 3. So, and the values of the function at this point, they are 10 to 1, because when n grows, t goes to 0, 1 minus t goes to 1, but this value of 1 is never attained. So we cannot speak about maximum, so this function does not attain its maximum, but we can speak about the supremum. So MAB is the set of all bounded functions on the interval AB. And we know that for every function f from MAB, since it's bounded, its supremum is finite. Supremum is finite. So on this set, we can define the raw infinity metric, which is the absolute value of the difference of two functions, and then we take supremum of this expression. In a similar way to the case of sequences, it can be shown that this is metric. So the first two axioms are quite straightforward, but for the third axiom, you should use the triangle inequality for the absolute value and the property of supremum. One more example. Let S be the set of all sequences, not necessarily bounded. Of all sequences. The set of all possible sequences. Alright, that's still the coordinates are x1, x2, x3, and up to infinity. So on this set, we cannot introduce row infinity metric because the sequences are not necessarily bounded. We cannot introduce p metric because they are not necessarily p-summable. So we take the huge set of all sequences. But there is a way to introduce metric on this set, and this is the way. So we take an infinite sum over all coordinates and we introduce a metric in this fairly fancy way. This 2 to the power k term is specifically plugged here to make this sum finite. So what we have first, we have well, we clearly have that xk minus yk absolute value over 1 plus the same expression is strictly less than 1, for sure. And so this function is less than or equal to sum of 2 to the power of minus k from 1 to infinity, which is a convergent series. So this metric is, well, this function is defined. So this series infinite sum is finite. Let's now go through axioms of metric. So the axiom 2 is the simplest as typical. So if we swap x and y, we swap it here, and by the properties of absolute values, we get exactly the same value. What about axiom 1? Axiom 1. So if we have row of xy equals to 0, then we get that all this infinite sum equals to 0. But every component of this sum, for every k, this expression is non-negative. So we have infinitely many numbers, sum of infinitely many non-negative numbers, and it equals to 0, which means if and only if each of these numbers is 0. Well, and from here we just conclude that this expression is 0, which means that xk equals to yk, which is exactly what we want. So done with axiom 1. The axiom 3 will be your exercise. As a hint, you can use that a over 1 plus a is less than or equal to b over 1 plus b if a is less than or equal to b. we had about 10 examples of different metric spaces, and now I will state a result which is the source of unlimited number of examples. So this is a proposition, but it is fairly simple. So if X raw is a metric space, and Y is a subset of X, then a pair Y raw is a metric space. Is a metric space. So we take a subset of the set X and consider it in a pair with exactly the same distance function, and it will be a metric space. In this case, we call this Y raw, this new metric space, a subspace. A subspace of X raw. So we have considered several examples with various functions on some defined on some sets, and we showed that these functions are metrics. So the question is, how crazy can the function be if it is a metric? So can it be any function? Of course not. It should be positive, it should satisfy some properties. But are these properties very restrictive? Are there a lot of functions which can be metric or not? Let us consider, another example. If a pair X raw is a metric space, and raw 1 is of xy is the square root of raw, then X raw 1 is a metric space. So if we take a metric and take the square root of it, then we will get the metric. Let's check it. Indeed. Well, the axiom 1 and axiom 2 are quite straightforward, because if this is 0, then this is 0. If we can flip it here, we just flip it here, and we get axiom 1 and 2 satisfied. The triangle inequality is the most interesting. Let's take 3 points and consider row 1 of x, z, which is square root of row of x, z. Row is a metric, so we can use triangle inequality for it. And now we can use the property of the square root. which is nothing but rho 1 of xy plus rho 1 of y. So it is in fact a metric. And I will state a couple of exercises for you to solve. If rho is a metric, then rho 1 equals to rho over 1 plus rho is a metric. Another one. Well, this one assumes of course that we are on an arbitrary set. If on some set rho is a metric, then rho 1 is the metric on the same set. For the exercise 2, we will be on R1. Rho of xy equals to arc tangent of x minus 1 and the absolute value of all this. So this kind of crazy function is a metric on R1. Is a metric on R1. And even more general, let phi be a twice differentiable, twice continuously differentiable, function on R1 such that we want it to be, well, we want to build a metric from this function. So first of all, we want it to be non-negative. We want first derivative to be non-negative as well. And we want the second derivative to be non-positive. So we just take this function phi and then prove that phi of an absolute value of x minus y is a metric. Is a metric on R1.